Hey listeners, a quick word before we start the show. It is Canary Media's birthday. That's right, Canary Media and Postscript Media are partners on these podcasts. They're turning one this week, and to celebrate, they're having a party, a donation party, and we're asking each of you to bring a gift. If you don't already know, Canary is a nonprofit news organization. Part of their funding comes from listeners like you, and your financial support ensures Canary's newsroom continues to cover the solutions to the global climate crisis, and it ensures podcasts like The Carbon Copy and Catalyst have a home. So please take a minute to go to www.canarymedia.com and click on the donation button today. We've got a link right there at the top of the show notes. Be part of the solution to the climate crisis and sustain fact-based reporting on the energy transition, because if not now, then when? And happy birthday, Canary Media. Let's make sure there's many more. Thanks.
From the studios of Postscript Media and Canary Media.
I'm Shayle, and this is Catalyst.
CCU and CCS is what you get to after you've run through most of these other things, because most of these other things are less politically contentious. They can be more or less costly, but it's stuff that, it doesn't attract a lot of fire.
The news of point source carbon capture's death is greatly exaggerated.
Let's face it, environmental news is often very depressing. That's why we focus on solutions on this podcast. But still, the climate crisis looms large. Rising temperatures, mounting pollution, environmental degradation, they're all warping the planet. And for a lot of species, including us, things don't always look so great. But the story doesn't end there. Every Friday, Living Planet, a show from Deutsche Welle, takes you behind the headlines to figure out what's happening and how we'll get through it. It'll also help you make better choices for a healthy planet and find space to reconnect with the beauty and wonder of the world around us. You can find Living Planet wherever you get your podcasts.
I'm Shayle. I'm a partner at the venture capital firm Energy Impact Partners. Welcome. Well, don't look now, but carbon capture, not carbon removal, but point source capture, is making a comeback. After a string of relatively high-profile failures and cost overruns, a lot of people basically wrote off the idea of capturing CO2 directly from flue stacks at industrial and power generation facilities. But don't count it out. The global capacity of planned CCS, carbon capture and sequestration projects, grew 50% just over 9 months last year to a total of 111 million tons, which would triple the current operating capacity in the world. Actually, the chart of planned projects in the world is kind of interesting. It looks like, if you can imagine, a U. A decade ago, even more projects were planned. There was a lot of excitement around point source carbon capture, but many of those were shelved ultimately after cost overruns and market conditions changed. But if you look at the past couple of years, we are climbing back the other side of that U. So why the recovery? And what are the critics? And what might happen this time? What role does point source carbon capture have to play in a deeply decarbonized future? Well, for this one, I spoke with Dr. Chris Bataille. Chris is, among other things, a researcher at the Institute for Sustainable Development and International Relations. He's a professor at Simon Fraser University. And most timely, he's the lead author on the industry chapter of the IPCC report that just came out this week. With no further ado, here's Chris. Chris, welcome to Catalyst.
Thank you very much for having me here today.
Excited to have you here. We're going to talk mostly about carbon capture and sequestration, but I want to start a little broader because it happens to be good timing, which is this big seminal updated IPCC report just came out that you had a big hand in helping to put together. There's a lot in it, obviously, and I'm sure many folks who are listening have read a bunch of the reporting. But from your perspective, what are the key takeaways that we all who care about this stuff should take from this IPCC report?
Yeah, sure. That absolutely. So the first thing is, we're out of time here, and that's been repeated over and over again. 20 years ago would have been good, 10 years ago, but now is better than 10 years from now. We're +1, and that's just too much. The second is, that's the bad news. The good news, however, is that the dramatically reduced costs for solar, for batteries, for wind, for electrolyzers, all this stuff is coming down way faster than anyone expected, which is transforming our expectations of what can happen. Also, there's a lot of progress being made on demand adjustment, material efficiency, thinking about the demand for everything and for materials, what have you, not just the supply.
All right. So in other words, it's really bad and it continues to get worse, but also we're doing all the things that we should be doing to deliver technology that can help at least dig us partially out of the hole.
Yep. We just have to move faster on market uptake.
Okay, well, let's talk about it in the context of CCS then, which is our topic today. I want to start a little bit with running through the history of CCS, because it's kind of a storied history, not always in a good way. And I think a lot of folks who've been in and around this space for a long time are, understandably skeptical because there has been this long winding road. I should say, first of all, that we're going to talk primarily about point source carbon capture, though I know we'll probably talk a little bit about direct air capture and alternative carbon removal technologies when we talk about the sequestration part. But tell me a little bit about the history of point source carbon capture.
Yeah, sure. No, absolutely. CCS got started because in the mid-90s, some companies that were working with methane and what have you needed CO2, and they just by themselves started separating it out and getting the CO2 out of it. And it worked. Like, it's just a technology, it's an engineering technology that works. Everyone got excited about this and immediately made this mental jump that, we can do this with coal electricity plants and, keep coal plants going globally, what have you, and we don't have to worry about coal. The problem is going from, breaking apart methane into its constituents as opposed to using flue gas from coal is a completely different problem. So we had these experiments through the 2000s up to 2010 where we just had a whole series of high-profile failures, partly because we were doing a much harder problem, which is, coal flue in the presence of nitrogen, coal flue gas in the presence of nitrogen.
Can you go one level deeper there? Like, why is it easier to separate the carbon from methane than it is to capture it from coal flue gas?
It's simply because we had this process. Okay, so first of all, when methane comes out of the ground, it's a mixture of water, it's a mixture of hydrogen sulfide, it's got CO2 in it to various degrees. You have to clean it. You have to get the hydrogen sulfide out, you have to get the carbon dioxide out, and use what's called an amine separation process in order to do that. And people thought you could take the standard amine separation process from gas processors and use it for the flue gas for coal electricity plants. The problem is, for most coal plants, what's coming out, it's full of garbage. Like, it's full of all sorts of contaminants, it's full of particulates, and it messes with the amine separation process. So you can't just straight off use that. And there were some very high profile and very expensive experiments where it just failed and they had to replace the amine solution over and over again. It's not a direct thing that we can do.
Okay, so we have all these high profile failures over the course of the past decade or so. But it feels like over the past couple of years, there's this kind of resurgence in interest, probably partially driven by demand for these big, heavy emitting sectors to decarbonize, but also because it feels like maybe the sector has learned some of those lessons. You can't just apply that same technology that we were using to separate, to clean natural gas, essentially, to then do carbon capture on coal plants. There's some difference, I think, in this current wave around what we are capturing, like what the point sources actually are. It's not all about coal. So maybe talk through a little bit what's happening now today and what's been happening over the past couple of years.
Yeah, no, absolutely. The first high-profile success was the Sleipner offshore platform in 1996. But it was the Norwegian, it was Statoil at the time. It became Equinor, and driven by the Norwegian carbon tax, their gas processor there was stripping out the CO2 and re-injecting it into a deep saline aquifer below the gas producing layer. And they said at the time, we think it might cost us $60 a ton. reportedly, it's been about $15 to $20 a ton operating life is what it's actually costed. Now, we could have been doing this with gas processing, give it lag by 5 years. We could have been doing this across North America, but we didn't require it. Right? Or it got into a big tussle about who should pay for it, how it should get done, what have you. But the core thing is that Equinor was working with a concentrated flow of CO2. So anywhere in an industrial process where you're getting out pure CO2, you can compress it and push it back down underground. So fertilizer plants could have been doing this by now. Ethanol plants could have been doing this by now. And there's a really interesting project company in Texas called Net Power that is getting pure CO2 out of the back end of an electricity generation plant, but it's because the working fluid is not air. It's actually compressed supercritical CO2. So they inject methane, they inject oxygen, they ignite it. You get the standard thing of it's water and CO2, but they bleed off the CO2, and then their plan is to sell it or re-inject it underground, and it works.
So let me try to reiterate what I think is a core point here, which is the concentration of the CO2 in the flue gas is core to the economics and the viability of point source carbon capture. There's some places where you get really high concentration CO2 that then can lead to, as you said, capture costs in the $15 to $20 a ton range, which is really cheap. But if you have low concentration CO2, much more difficult to separate.
Yeah, it's the concentration and the cleanliness. So the amount of particulates and other contaminants that come out with it. But that's the essence of the problem.
So then meanwhile, you said we could have been doing this with ethanol plants and ammonia plants and stuff like that for the past 20 years. We had not been, but it feels like we may be coming up. Like, what's the current state of affairs?
I think we're on the verge of doing that, right? The 45Q tax credit in the US and similar credits that are developing in Canada and what have you. I think we're on the verge of these things being reapplied. There's still a tussle about who pays for what. And I think politicians have been a little afraid just to mandate. Like, if we just gone with a mandate and the companies could cost it back in the rate base for gas and what have you, it would have just happened. The problem is we're allowing this to be a negotiation, and we're not requiring it and then compensating them for their extra costs.
Although the 45Q tax credit, which is a $50 tax credit if it's not used for enhanced oil recovery, that's well in the money for some of these higher concentration sources now. So you think just purely economically, like, why not do this? If you can get a $50 tax credit, cost you $20 to do, that's good margin.
Yeah, no, it's a good question why it's not going ahead. Like, why did Equinor go straight to that as a state oil, a very advanced state oil company, and they had no problem doing it at several of their facilities? Whereas we seem to have trouble with it in North America? I haven't got a complete answer to that question.
I want to talk about the sequestration side. There's one question: can we economically capture and separate CO2 from some industrial process? And then there's another question: what do we do with that CO2 afterwards? Mm-hmm. What is the current state of affairs? And this, by the way, this applies to point source capture, but it also will apply equally to direct air capture. And if we're going to do things like bioenergy with CCS, BECCS, so to speak, it feels like whichever of these scales fastest, we're going to end up with a lot of new CO2 that needs to be sequestered somewhere.
There's where the rubber kind of hits the road. There are a few things that we can think about making products out of the carbon, graphene, what have you, but there are a lot of different potential sources of carbon. One of the big things with oil sands, I'm Canadian, by the way, with oil sands is they want to move into making graphene from bitumen, like non-combustion uses of bitumen. So there's a whole other discussion we could have there. But the problem is once you get going with this and really start doing this with gas processors, ammonia, ethanol, other parts of the chemical industry which have concentrated flows, that's a lot of CO2 you got to get rid of. The first biggest application that actually reduces emissions if you do it properly is enhanced oil recovery, because you're pushing it down, you're using older wells, you're pushing the CO down to increase the miscibility and repressurize the well, and it's far less emissions intense than, say, offshore or oils. Offshore is actually low emissions, but oil sands and what have you. But you have to make sure that the well stays tight afterwards. It's the well management really so There's a whole literature on this. The first biggest impact use, if you're going to do CCU, is actually enhanced oil recovery in place of other higher emitting oil sources as we climb down from 100 million barrels a day down to zero sometime mid-century. But, obviously that's a contentious thing to say.
Well, so let me see if I can unpack this for a second. So various ways to capture CO2. You can either capture it from a point source, you can capture it from the atmosphere, you can separate it from biomass. Either way, you end up with CO2 gas that you need to do something with. And your options are either to utilize it for something, that's the U in CCUS, which I wasn't referring to quite yet, or you sequester it. Now, enhanced oil recovery is sort of in between, right? You're kind of sequestering it in a utilization play,
Yes.
so it sort of feels like it's some of both. But what you're saying is that in the context of utilization, if you're going to use the CO2 to do something, actually the earliest, most economic play is for enhanced oil recovery, which is really controversial. But also, there's been a bunch of news recently around the first really big direct air capture plants that are getting built in the US that are getting built by this company 1.5, which is a JV between Carbon Engineering and Occidental Petroleum. And those are all, it's a 1 million ton per year plant, the first one that is being used for enhanced oil recovery, to your point.
Yep. No, because all the finance adds up.
Right. There are other ways to utilize CO2, right? You can put it into concrete. There are some other products you can convert it into other chemicals, right? And so the challenge that I think a lot of people have, which I think is what you're referring to, is that getting that may be great to do, but given the scale of the CO2 capture that we will need, it's tough to imagine utilizing most of it in those applications.
The numbers I typically see is we will utilize less than 10% of it. Most of it has to go into deep storage, be it depleted oil and gas reservoirs with tight overseal or into deep saline aquifers. Like the vast majority has to go into permanent storage without utilization.
So let's talk about the latter of those two, deep saline aquifers. How abundant are they? How hard are they to access? What are the barriers to us taking gigatons of CO2 out of the atmosphere or from power plants and putting them underground?
Yeah, there's a lot of, you'll see a lot of conflicting numbers about deep saline aquifers. They typically underlay most sedimentary basins globally. So where you find oil and gas, you go a layer deeper, that's where you find the deep saline. So generally, if you're bringing up oil and gas, there's going to be a deep saline aquifer somewhere near you that you can use. But you have to drill deep, which means that you have to compress. So there's going to be an electricity cost compressing to get it in there. But once it's in there, there's thousands of like the number that goes around, the utilizable number is roughly 1,000 gigatons, which is more than the current budget for 1.5C. And the IEA says something like 2,000 to 3,000 gigatons, and really there's probably tens of thousands of potential deep saline aquifers available globally.
What about other mechanisms to sequester, like mineralization? Right, this is the sort of big Climeworks facility in Iceland is doing this. With a company called CarbFix. How do you think about that compared to just injecting underground?
Eventually, that's actually what happens with deep saline aquifers. The CO2 binds to the geology, so you eventually are getting carbonation and mineralization going on. There are many different ways you can like CO2 is an acid. It's going to combine with a whole bunch of different things. And they literally, there are these mountains of olivine in Saudi Arabia and in the Arabian Peninsula. And they talk about cracking up the olivine and exposing it, and it will carbonate with the CO2 in the air. It's just awfully hard to measure how much actually works, but it's cheap and it does work chemically.
So do you think that sequestration capacity will be, I understand sort of technically that there's not really a limitation there. Do you think practically speaking, is that going to be a bottleneck to either point source or direct air capture in the next decade?
I think there's going to be some resistance there, partly just socially. After the experience with the shallow fracking that brought up a lot of methane, people are worried about drilling, right? So deep saline is you're going 800 meters down. There's not going to be a problem if you properly do the well casing. But you're going to have stakeholder issues there. In Alberta, they just let out a bunch of the deep pore space, to a cement project that's going ahead right now. But you do have to run through a process. But partly in Canada, it's because the pore space base belongs to Canada, to the Crown, whereas I believe in the U.S., it mainly the subsurface rights belong to the landholder. But again, that's going to be different by jurisdiction.
Let's talk a little bit more about the point source capture technology. I mean, you mentioned that sort of the amine solution that was being used for separating out methane isn't the right fit. What are we doing now? What are the different ways to capture point source emissions today?
Yeah, there's a bunch of there have been lots of improvements on amine since. And the thing is, if you have a clean gas you're working with, a clean flue gas or methane or some version thereof, it works just fine. The problem was going to coal and coal flue gas. That kind of, we ran into a bottleneck there. People have experimented with lots of different versions of amine solutions. There's talk of moving to ceramic filters, polymer filters, what have you. So it uses the partial pressure of the gas, so the CO2 travels across the polymer membrane, but the rest of the gas goes another direction. But a lot of this stuff is very low TRL. There's nothing that's really. I've heard of cyclones being used to separate CO2 from nitrogen and what have you. But again, a lot of this stuff's very amine versions of amine separation are still our main way forward, and which means that you're sticking with clean feedstock to feed the process.
Let's talk a little bit about cost then. I mean, you said there's some applications in which we think we can do capture for, and this is just capture, not including storage and sequestration, for $15 to $20 a ton. Is that right?
That the separation had to be done on the Equinor platform to get it out of the gas. So that cost is not in. That's just industry standard, because natural gas, the gas in our pipes has to have less than 2% CO2, or it starts eating things. That $15 to $20 is the recompression, the drilling recompression, and down to the saline aquifer and monitoring. That's what the 15 to 20 was. And again, they initially estimated $50, $60 per ton.
Yeah. So what are like benchmark costs aside from those applications where it has to be separated out anyway? If you were to attach carbon capture to a flue stack at a big industrial plant, what kinds of costs would we expect to be looking at?
Again, it depends on the partial pressure. It depends on the partial pressure and the concentration of the CO2. There's a cement plant in just south of Edmonton where they're trying to put 95% capture onto it. Probably the number is in the range of $120 to $150 a ton for this first of a kind application, and that includes everything. That's capture, separation, transport, and recompression back into the ground. Typically, the numbers we work with is if you've got pure CO2 to work with, you probably have $40 to $60 per ton. But if you're doing post-combustion with a clean flue gas, probably the nth application will be $80 to $100 per ton. It's $80 to $120 per ton.
How do you think about the role of point source carbon capture, right? Like, you can think of it as being the solution, and this maybe gets back to the IPCC report, which I know has something to say on like which sectors do we need it in, and how important should it be relative to fuel switching or relative to carbon removal and direct air capture or all the other things that we can do. It's always a contentious debate to figure out, should we be attaching carbon capture to point sources? So how do you think about the role it should play?
This was an interesting and long discussion we had in the industry chapter, because we had all these strategic options and how do we frame it and how do we discuss it. And around the middle of the chapter, before we got into detailed scenario results and what have you, we framed it up as demand decarbonization and production decarbonization, right? So you're adjusting demand, you're doing material efficiency, you're introducing circularity, more recycling, what have you. Then you get into energy efficiency and fuel switching. CCU and CCS is what you get to after you've run through most of these other things, because most of these other things are less politically contentious. They can be more or less costly, but it's stuff that it doesn't attract a lot of fire. Where we focused is like we tried to give policymakers guidance. Where do we absolutely are we going to need CCS? We're going to need it for cement, because there are no alternative chemistries coming down the pipe anytime soon. And there's a lot of buildings that need to be built. So we need to figure out how to make basically zero emissions clinker that gets ground up and mixed for cement that holds concrete together. The other sector is chemicals. Chemicals is the fastest growing industrial sector. While demand's roughly flat globally for steel steel and cement. With chemicals, it just grows and grows and grows and grows. Like there's just no end to it, in sight or level, any sort of saturation. So we need to figure out and most chemicals are a carbon lattice wrapped around 1 degree to 1 degree or another by hydrogen and oxygen in various forms. So we need to sort out how to, can we use waste carbon? Can we use biomass carbon? Can we get direct air capture carbon to sub in for the fossil fuel carbon that was used there? So, use waste, recycled, what have you. So we think about things in that order. And when you think about the things in that order, there are two sectors that actually absolutely do need CCS. That's cement, the right up front part of cement, and chemicals, and specifically for plastics.
You're leaving out, obviously, the power sector, where there have been some of these big kind of like high-profile cost overruns and timeline overruns and things like that for CCS in the past. Do you think there's a role for CCS in the power sector? I mean, you mentioned net power, which is a version of that. Do you think that you can maybe describe that one in a little bit more detail? And then, do you think that's a scalable opportunity in the power sector?
No, absolutely. The reason I left out power is because I was trying to think of in most regions, where do you need to think about CCS? And for me, that's cement and chemicals. I think CCS is going to have an application in power for firm clean power underlaying the variable system. So I'm sure, I think you had Jesse Jenkins on your show a little while ago, right? Where it's, yes, by far the cleanest sources of bulk power are going to be wind and probably solar going forward. But as you raise the levels of that and the variability starts kicking in, you need firm clean power to underlay it and, set a cost base, right? And that can come from many sources. It can come from hydro if you have access to it. It can come from stored hydrogen that's then reprocessed back through a turbine or a fuel cell. It can come from small or large nuclear, but it can also come from fossil fuels with CCS. And net power, to my mind, is one of the most promising because it goes around the problem of trying to solve post-combustion CCS. It goes straight to a concentrated flow, which we know how to dispose of today.
So you mentioned the sort of why CCS is often politically contentious. Let's talk about those reasons in particular, and I'm curious how you think about them. I think of two generally. There's probably more. The first is that you don't solve anything to do with upstream emissions if you do CCS downstream. So if you're doing carbon capture on a natural gas fueled process, then the upstream methane emissions from basically the entire value chain are not solved by doing CCS. How do you think about that, and how do you incorporate that into your thinking around the role of CCS in these sectors?
No, that's a really good question, and I'd have to preface that with as a Canadian, I'm one of the first people that introduced the whole electrify everything discussion into our policy debate, right? And so you go traveling through transport and traveling through light industry and buildings, what have you. But you always come back to heavy industry and you come back to the oil and gas sector. And if we have a fundamental problem with fugitives globally. Every time we look harder, every time we put more refined measurement on this, the numbers go up and up and up and up. Now, it's highly variable by practice. We know how to do virtually zero fugitive or upstream oil and gas extraction, and they do it in the offshore because of the fire risk. However, in places like the Permian, where the number is 7%, then 8%, then 9%, those are tragically high fugitive levels. You might as well be doing coal. So the question is, we know how with existing technologies to do less than 0.5% fugitive rates for everything, right? And that should be the benchmark, to my mind, by the 2030, because we're at 100 million barrels per day and a large consumption of natural gas. That's going to be with us for 30 years. We have to cut the fugitive emissions, and we know how to do it. Just do it, charge it back into the rate base, and the higher costs will translate into lower demand. So it's just an a priori thing for me that we have to bring fugitives down to first to less than 1% and then to 0.5%.
And then I guess it's sort of the related but slightly separate question around CCS as an approach is that it locks in the use of fossil fuels when some people would argue we need to be getting off of fossil fuels as fast as humanly possible, and so we shouldn't be doing anything to perpetuate their usage, which CCS is perceived to be. Do you think that argument holds water?
If we were trying to do bulk use of coal with CCS and just carry on with natural gas, I think that might be a problem. But in my space, it's about cement process emissions. It's about chemical process emissions, and a little bit of net power gas to firm up a mainly wind and solar power system is not going to lock in a whole lot of oil and gas production. It's that argument applies if you're trying to preserve the existing consumption of coal and gas, which to my mind is not supportable.
I'm just realizing you mentioned that the two sectors that you think are really going to need CCS are chemicals and cement. But we also talked about the sectors that are deploying CCS right now, which tend to be ethanol and ammonia, ammonia is a chemical, but not cement. We mentioned at least, right? Is there a divide there? Why aren't we doing CCS on cement plants now?
No, that's an excellent question. And I have a lot of contact with the Canadian cement industry and the global cement industry, and they want to do it because it's challenging because they actually have to do post-combustion, but it's at a very high concentration. So if we're going to make a breakthrough in post-combustion CCS, it will likely be in the cement sector. And there are 3 pilots happening that are built, high capture pilots happening right now. We'll make the breakthrough there, and if it's easy, we'll start to apply it to other sectors. But in the end, we'll probably just keep applying it there. Now, for ammonia, there may in the short run be an argument for using blue hydrogen to make ammonia for fertilizers. But in the long haul, like past 2030. Really, the cost of electrolyzers and the cost of solar, you would make fertilizer where green electricity is cheap. You wouldn't try to make it where there's hydrogen with methane and CCS.
All right. So the final question, do you think that we'll end up using CCS as a way to get net negative emissions from various industries? Is it going to be an both and rather than either or as we think about doing carbon capture and also fuel switching and also direct air capture, whatever else it might be?
The optimist in me would love to see the IEA's net zero 2021 scenario come around where there's a minimal amount of CDR happening. We hit near zero by 2050, and there's just a little bit that has to be done. But the realist in me says that's not going to happen. We're just emissions keep rising. We have these coordination problems. We're probably going to blow past the deadline by about 2 decades, which means, CDR is basically an admission of failure that we did not mitigate fast enough. Also, we've emitted too much already. We're already over budget. So yes, we're going to need technical CDR. I'm somewhat dubious about bioenergy with CCS just because of the land use requirements and that we're tight for land anyway. We need it. We need it for food. We need it for a space to live. We need it for biodiversity. We need it for all sorts of other things before we start talking about bioenergy. So the key CDR technologies in my mind will be direct air capture with CCS, because what CCS does is it takes the CO2 taken by the direct air capture unit and pushes it back underground, and probably some forms of geological weathering. And it's going to be a big business. Like we're talking minimum at least 1, 2, 3 to 5 gigatons per year. And if we really slow on the mitigation, we've got to go north of 10 to 20 gigatons per year to get the cumulative CO2 under control.
What else would you leave as a takeaway for folks who are listening today on CCS?
CCS is neither bad nor good. It's a tool, right? And it's a complex tool with shades of gray attached to it. And you need to, when you listen to debates about CCS, you need to know about the details, the differences in concentration, concentrated flows versus post-combustion. Concentrated is commercial today. Post-combustion is not. We're going to need some CCS for certain sectors, but if somebody tells you that we absolutely need CCS for steel, that's just not the case.
Chris, thank you so much for being here.
Oh, my pleasure. Thank you very much for having me.
Chris Bataille is a researcher at IDDRI, the Institute for Sustainable Development and International Relations, a professor at Simon Fraser University, and a lead author on the industry chapter of the IPCC report that just came out. This show is a co-production of Postscript Media and Canary Media. Find the show on Twitter at @CatalystPod. You can also find me or Postscript or Canary there as well. Tag any of us to send feedback on this episode or to suggest future topics. If you liked the show today, Go over to Spotify or Apple Podcasts or wherever you get your shows and leave us a rating and review, or share the episode with a friend. You can find links for this episode's topic and guest in the show notes at canarymedia.com. Postscript is supported by my friends at Prelude Ventures, a venture capital firm that partners with entrepreneurs to address climate change across a range of sectors, including advanced energy, food and agriculture, transportation and logistics, advanced materials and manufacturing, and advanced computing, and they probably forgot a few in that tagline. The producers for this episode were Daniel Waldorf and Stephen Lacey. Our managing producer is Cecily Meza Martinez. Mixing by Greg Vilfrank and Sean Marquand. Theme song by Sean Marquand. I'm Shayle Khan, and this is Catalyst.